Let's solve a question related to the basic computer. So the question is write a sequence of micro operations needed to define the execute phase of the following instruction in the basic computer. So SBM is the symbolic name of the instruction, and this instruction is to be defined for performing subtraction. So here a memory word is required to be subtracted from TR, the temporary register available in the basic computer. The result of subtraction is required to be made available in the same memory word M of AR. The opcode for this instruction is also given, that is 011, and one constraint is also specified, that is the content of AC cannot be changed unless it is specified in the instruction. This means if AC is not specified as the destination register in the given instruction, then you have to ensure that the original value available in AC is restored at the end of the execution. So, this is the information given in the question. Now, let us see how to give the required sequence of micro operations. So, let us start with identifying the type of the instruction. So, here, if you read the description, the opcode is given. 011 is the given opcode. Now, if you recall the basic computer's configuration and the set of instructions available for the basic computer, you can easily identify that this is the opcode for a memory reference instruction. For register reference or IO, the opcode must be 111. As it is not 111, it must be an opcode of a memory reference instruction. If you do not use this logic, then also it is possible to identify the type of the instruction. uh, so this is the actual operation to be performed. So as a memory word is involved in the execution of the given task, it must be a memory reference instruction. Determining the type of the instruction is important for such questions because here you have to decide from which timing signal the execute phase will start. You are required to give the logic for the execute phase only. You are not required to give the logic of the remaining instruction cycle phases. Okay, so as we have decided that this is a memory reference instruction, the execution will start from time t4. Now, if you want to define an exact control function for the execute phase, the steps of the execute phase, then you have to consider the decoder output as well. In the basic computer, a 3-bit opcode is interpreted using a 3 cross 8 decoder available in the control unit. So if you give 011 as the input to this 3 cross 8 decoder, the output would be D3. That means the D3 output pin will have a 1 and rest of the outputs of the decoder will have zeros. So D3 can be used to form control functions for this instruction. So D3 T4 would be the first control function for the first micro operation for the execute phase. Okay. Now here we also have one constraint, and that is we cannot change the content of AC. As AC is nowhere mentioned in the instruction, if you use AC for some intermediate calculation, you have to restore uh, the original content back in AC at the end of the execution. So let us see how to proceed. As you know, in the basic computer, memory words cannot be processed directly. So, if you want to perform any operation on the content of a memory word, you have to read that value usually in the data register DR. So, let us start with that logic. So, the first micro operation should be M of AR to DR. Now, actually, this M of AR is the subtrahend for the given subtraction operation. As subtraction is not directly possible to perform, what you can do, uh, you can find 2's complement of the subtrahend and add it to the first operand. So this should be m of ar dash plus 1. This will be the 2's complement of the subtrahend. Once you have this value, you can add it to tr to get the result of subtraction. So we have already read m of AR to DR because it cannot be processed directly. Now what is the next thing to do? As you want to find one's complement of this m of AR, which is currently residing in DR, you should transfer it to AC, because one's complement is a unary operation, and for unary operations the basic computer by default takes AC as the input. So what you need to do here, you have to transfer this dr to AC so that you can find one's complement of this value. Now you have to also keep this constraint in mind that AC cannot be changed. So when you transfer dr to AC, at that time you can also initiate this operation. The previous content, the original content of AC, can be stored in a memory word. We will not transfer AC to DR because TR is the other operand, and TR cannot be directly loaded into AC because AC does not receive any inputs from the bus. So eventually you have to transfer TR to DR. So you cannot keep the content of AC in DR. And obviously you cannot transfer it to TR because TR is going to be used for providing the first operand for the operation. So you can transfer the content of AC to some memory word. Obviously the same memory word because we are using the same address AR here. Okay. Now you have, when you try to execute simultaneous operations, you have to also ensure that there is no conflict. Conflicts can be of two types. Either it can be a data conflict or it can be a resource conflict. So here, DR to AC, this transfer will take place via the adder and logic circuit, and AC to M of AR, this transfer will take place via the common bus. So there is no resource conflict. If both the operations are using bus or if both the operations are using the adder and logic circuit, then there will be a problem, and in such cases, simultaneous execution is not possible. So here there is no conflict, so this can be done. Now let us also write the control function associated with this operations. So it would be D3T5. Note that the decoder output will remain constant till the end of the execution. Only timing signals will change. Okay. So what we have done so far, the second operand is currently available in AC. So in the next clock cycle, you can find its ones complement. You have also preserved the value of AC in the memory word. Now, the next timing signal would be T6, and that's why the control function would be T3 T6. Now, what do you need to do? The first operand is still in TR. If you want to add 2's complement of the subtrahend to the first operand, you have to read TR to DR because the addition is possible only on the content of AC and DR. So TR can be transferred to DR using the common bus. Now, once this value is available in DR, you can think of adding the 2's complement of the subtrahend to this value. So let us utilize this time as the common bus is occupied for this transfer TR to DR. Simultaneously, you can start complementing AC. You want to find 2's complement of the subtrahend, so that is again divided into two parts. First find 1's complement of it and then add 1 to it. So this complement operation will be performed by the adder and logic circuit. The value required for this complement operation is AC. The result will by default go to AC, and here the other part of the operation involves TR to DR transfer. So here also check that there is no conflict. So TR to DR involves the common bus, and this second operation involves the adder and logic circuit. Values are also not conflicting, so this is fine. Then comes the next timing signal T7. Now your first operand is available in DR, and you have already found one's complement of the subtrahend. You have to add 1 to this one's complement value to make it two's complement of the subtrahend. We cannot initiate any other operation during this time because the adder and logic circuit will not be used here. Actually, this increment can be done by enabling the increment control input of the AC register. Most of the registers in the basic computer have load, increment, and clear control inputs. So adder and logic circuit is not involved in this. Even the common bus is free if you want to initiate some transfer, but here we have value dependency. Until and unless you have this two's complement of the subtrahend, you cannot initiate the next operation, that is addition, adding this two's complement to the first operand. So you have to wait until you have this value available in AC. Okay, the next timing signal would be T8. So now two's complement of the subtrahend is ready and it is available in AC. You can add it to the first operand which is currently residing in DR. This addition will be performed by the adder and logic circuit, and by default the result will go to AC. As this is addition, there is a possibility of having one extra bit in the result, and that you can store in E flip flop, the extended AC flip flop, in case some output carry is generated. Now, the subtraction is done and the result is currently available in AC. If you look at the question, the result of the subtraction is required to be stored in a memory word. Now, during T8, you can obviously not initiate this transfer AC to M of AR because you have to wait until the result is fully available in AC, and that will take approximately 1 clock cycle time. Usually, any operation that you perform using the adder and logic circuit takes around 1 clock cycle time. So you have to wait until the final result is available in AC. But you have to also restore AC because now the subtraction is done. So you have to restore AC, the original value of AC in it. Now, where this value is currently available, it is available in a memory word. So what you can do here, along with this addition, you can initiate this transfer M of AR to AC. According to the configuration of the basic computer, M of AR to AC cannot be done directly because AC cannot receive any inputs from the bus. So you have to first transfer M of AR to DR. M of AR to DR, this transfer will take place via the common bus, and for this addition, you need initial values, whatever values are available at the beginning of this timing signal or clock cycle, and that's why there will be no conflicts in the values. So here the bus is involved, here the adder and logic circuit is involved. So there is no data conflict, there is no resource conflict. Okay, now let us consider the next timing signal, that is T9. So now you can initiate this transfer AC to M of AR. This will happen via the common bus because AC can send its content to other registers using the bus lines. So your final result of subtraction will be available in M of AR. The given operation is complete. Still, you need to restore AC. So the original value of AC is currently available in DR. You can initiate this transfer DR to AC along with AC to M of AR. These two operations are not conflicting because for DR to AC, the adder and logic circuit will be used, and for AC to M of AR, the bus will be used. So this is the end of the operation. you have to reset the sequence counter so that uh, a new series of timing signals can be generated for the next instruction, and for that you have to set the sequence counter to 0. Write the exact control functions for each clock cycle. So this sequence of micro operations is needed to execute the given SBM instruction in the basic computer following all the required constraints.